Good morning, everybody. Thank you very much for inviting me to the Northeast Summit. My name is Dr. Benoit Desjardins. I'm professor of radiology at the University of Pennsylvania. My talk today will be on the promises and challenges for artificial intelligence in medical imaging. In 2016, Goeffrey Hinton made the following extremely important remarks at a conference.
Let me start by just saying a few things that seem obvious. I think if you work as a radiologist, you're like the coyote that's already over the edge of the cliff, but hasn't yet looked down, so doesn't realize there's no ground underneath him. People should stop training radiologists now. It's just completely obvious that within 5 years, deep learning is going to do better than radiologists, because it's going to be able to get a lot more experience.
Professor Hinton is not a clueless person making assertions without thinking. He is a fellow of the Royal Society in England, a British-Canadian cognitive psychologist and computer scientist, and is known as the Godfather of AI and the Godfather of deep learning. His statement that you just heard shook the field of radiology to its core and started a lot of discussion and initiatives. Well, we're now in 2021, 5 years after his famous talk, and I've still not been replaced by a computer. But in those 5 years, there has been tremendous development in AI applied to radiology. There have also been many bumps on the road. Here's, for example, an AI algorithm pretending to diagnose pneumonias on chest x-rays from several institutions. At first, it seems to work very well. But when heat maps were generated to figure out the key features of the images helping the diagnosis, they pointed to markers on the top right corner of the images. It turned out that the AI algorithm had exploited a confounder, a marker on the x-rays which was different between two hospitals, and most of the positive images were acquired at hospital number 1, and most of the negative images were acquired at hospital number 2. It found an imaging features which was not relevant to the clinical diagnosis. The algorithm produced great results, but was actually incapable of recognizing the features of pneumonia on chest x-rays. My talk will be divided in 4 parts. First, I will explain why we need AI in medical imaging. Second, I will provide a brief overview of the basic concepts in AI. Third, I will show how AI can help medical imaging. Finally, I will discuss why AI has not replaced medical imagers. Why do we need AI in medical imaging? The profession of radiologist has dramatically changed over the past few decades. Radiologists are physicians who interpret medical images. When I was born, radiologists mostly interpreted plain radiographs. CT and MRI had not been invented yet. It was a 9-to-5 job during which they interpreted about 250 images. They were allowed to take breaks during the day to go eat and do other things. Today, the profession of radiologist is completely different. Everything is computerized and medical images are strictly digital. US radiologists are forced to interpret 1,000 times more images every day, non-stop, as fast as possible, working from 7 a.m. to late at night, with no possible breaks for eating and barely any bathroom breaks. It has become a miserable profession in the United States. Radiologists have now become completely essential to the functioning of hospitals. More than 95% of patients in hospitals have medical imaging done, as imaging has become the key for almost all diagnosis and treatment. There has been an exponential rise in demand for medical imaging, with rapid reporting of large volumes of images required. This has led to a massive burnout of the profession, with 60% of non-interventional radiologists being burned out and 70% of interventional radiologists being burned out. radiologists opt to retire very early, and the profession has become less attractive to physicians, making recruitment of new radiologists very difficult, worsening their current staffing shortages. We desperately need AI to help with a massive amount of work. Now, computer-aided detection and computer-aided diagnosis have been used in radiology for decades, especially for breast imaging. But they provided very limited benefit in improving diagnostic performance of radiologists. You could increase sensitivity of the algorithm to detect all potential lesions, with dozens of false positive lesions wasting radiologists' time, or decrease sensitivity of the algorithm to detect the most obvious lesions, but potentially missing more subtle lesions. But there's a big difference between computer-aided detection in those days and modern AI. Computer-aided detection used pre-specified features to identify suspicious findings on images based on human thought processes. AI, on the other hand, can detect patterns imperceptible to humans with high predictive accuracy. This is a completely different ballgame. Let's talk about the basic concepts in AI. AI is simply the replication of human intelligence in computers. A huge area of interest these days is machine learning, which is the ability of a machine to learn using examples instead of hard-coded rules. A portion of machine learning is called deep learning, which uses neural networks with many layers, the currently hottest area of AI applied to medical imaging. How does machine learning differ from traditional computing? In traditional computing, you simply give a computer a set of recipes, instructions on how to solve a problem. So you have specific code to convert inputs to outputs. Machine learning gives computers examples, sets of cases to solve a problem. The algorithm will find pattern in the data. What are the requirements for deep learning? First, you need fast computer hardware. This has become widely available these days, especially using gaming computers and very fast graphic cards. Second, you need big data, lots and lots of data, hundreds or thousands of cases to make the system learn. Third, you need new models and algorithms, typically in the form of complex networks, that can be reused in different contexts. The current availability of all three of these elements has made deep learning a very attractive field these days. How does it work? Well, this is based on brain function, which involves a network of nodes connected by links. These nodes receive inputs and produce outputs. There are different kinds of configurations of networks, and each configuration is used for different kinds of problem. For example, there are fully connected neural networks where each node is connected to the next. These are good to predict outcomes from unstructured data. There are convolutional neural networks, which are the most common in medical imaging and can extract features independent of their position in images. There are fully convolutional networks, which are like convolutional networks but producing full images. These are great for segmentation tasks. There are recurrent neural networks, which partly feed their own output back as input. These are great to process sequential data like ECGs. Finally, there are generative adversarial networks, which are good at generating realistic images. If you see fake videos on the internet, these have been generated using these networks. They are good for image enhancement. There are many other network configurations, but these are the main ones used in medical imaging. As I said earlier, neural networks involve a network of nodes connected by links. The link connecting each input to a node is associated with a number called a weight, which is proportional to the strength of the connection. Each node is associated with another number called a bias, which reflects an activation threshold. A sigmoid function relates the inputs to the outputs. How can neural networks learn from data? Here you have a system that learns how to discriminate between cats and dogs. So you give an input, say a dog, and a network evaluates the catness of the input and the dogness of the input. If you start from scratch with a dog as input, the network can give a catness value of 0.75 and a dogness value of 0.42. But the dogness value should be 1 and the catness value should be 0 for that specific input. So the error of the output of the network is computed from the expected output, and this error is fed back into the network to update the links, enabling the network to learn from its mistakes. By providing more examples, the network becomes progressively better at discriminating between cats and dogs. The most popular neural networks for medical imaging are called convolutional networks. These networks are made up of many layers, each performing a different function. Some of these layers are convolutional layers of processing to find specific patterns in images independently of their position. Other layers will perform different operations, such as reducing the size of images. These patterns are identified by performing a mathematical operation involving a filter. The filter represents the pattern to find. Convolution is simply a multiplication of the filter with all the parts of the images. And the greater the local result, the greater the match between the local image and the pattern in the filter. Now, what's absolutely brilliant is that the filters can be learned by the neural network. If you use a multi-layer network trying to recognize human faces, after you train the network, the filters at different layers converge to something that is absolutely fascinating and almost magical. The filters in the lower layers will represent tiny parts of images like edges. The filters in the middle layers will represent bigger portions of images like a nose or mouth. And the filters at the higher layers will represent different faces. And it's important to realize that these are converged to automatically by the neural network, and of course will depend on the inputs to process. If you're giving human faces as input, then it's going to generate filters like that. If you give hearts as input, then the filters will represent different parts or different configurations of hearts. So the same networks can be used with many different kinds of data. The way the filters converge is supposed to be similar to the way that a brain works. How can AI help medical imaging? One of the main foci of AI in medical imaging is to try to improve disease detection and minimize the identification of false positives. Rapid, correct detection of diseases by AI leads to earlier diagnosis. This leads to faster treatment. There has been work on the application of AI techniques for every single step in the imaging pipeline, from decision support all the way to prognosis. This leads to a decrease in turnaround time for critical findings and a decrease in radiologist workload. There are many clinical applications for AI in medical imaging. In our first step, AI can be used for the purpose of detection, to identify the existence of specific lesions on images, such as a lung nodule. In a second step, AI can be used for the purpose of segmentation, to identify the different parts of an image and determine the extent of lesions. AI already provides great tools to handle simple, tedious tasks more consistently, such as drawing contours or making basic measurements. In a third step, AI can be used for the purpose of classifications to try to come up with a specific diagnosis for a lesion. AI can also be used to register 2 or more images, to generate images, to enhance images, to retrieve images, and to assess image quality. This is a real product that uses AI to post-process 3-dimensional cardiac echographies. It extracts each of the 4 cardiac chambers automatically over the entire cardiac cycle to generate precise measurements of cardiac motion and ejection fraction. It does that processing in a fraction of a second. Here's an example of a real convolutional network that segments cardiac MRIs. This network contains 300 layers and 1 million parameters and was trained using 60,000 sets of images. The final product is a segmentation of different cardiac chambers and myocardium. So lots of complexity, lots of parameters, lots of hidden layers, but it does a really good job. There have been a few projects on computer tomographic angiography. Coronary CTA can identify coronary artery stenosis, but it's not always easy to determine which stenosis are hemodynamically significant. Computational fluid dynamics-based CT fractional flow reserve can tell you which stenosis are hemodynamically significant, but this is very demanding computationally. A new AI version of CT-FFR was developed and tested on many patients at many institutions. The results were really impressive. The AI technique was much faster than the computationally intensive CFD-based technique and produced similar results. Both techniques produce better results than visual assessment of CTA images by radiologists. Why will AI not replace radiologists? Although AI technology has improved exponentially over the past few years, there are still several problems preventing it from fully replacing radiologists. The first problem is the lack of transparency of AI algorithms. They behave like black boxes, producing a result, and we often have no idea of the process that the algorithm used to produce the result. Radiologists produce interpretations based on anatomy, physiology, and pathology taught in medical school, combined with well-known imaging concepts such as shape or local brightness taught during radiology residency training. A radiologist can explain specifically which imaging features he used to come up with a specific diagnosis. This improves confidence in the diagnosis, is teachable, and allows the next generation of radiologists to come up with the same conclusion. There's a lot of work to provide more transparency and explainability for AI algorithms. Two of those are very popular. First, AI system can display heat maps, which vaguely emphasize key imaging features which most influence the diagnosis. Second, AI systems can display learned prototype images of each category in a classification task. But this is far from providing an explanation based on anatomy, physiology, and pathology. AI has made a lot of progress, but it's far from being able to interpret images as well as humans or from being as versatile as humans. AI is already able to perform several visual tasks almost as well as humans, such as classifying basic images, driving cars, reading lips, or generating paintings. But of course, self-driving cars can still get involved in crashes. But so do human drivers. AI is already able to perform a few specific radiology tasks almost as well and sometimes better than radiologists, such as detecting pneumonia with the CheckSNet algorithm or diagnosing brain disease with the BioMind system. But these systems are designed to diagnose one or a few specific diseases, whereas a radiologist can diagnose thousands of diseases. As time progresses, AI will be able to diagnose more disease and handle more complexity. Or more likely, AI will involve hundreds of algorithms processing an image, each algorithm able to handle one specific task very well. AI might be able to eventually equal or even surpass the imaging interpretation abilities of radiologists. But radiologists do much more than simply interpret images. They interact with patients during medical procedures, such as biopsies or drain placement, interact with patients in regular imaging studies such as ultrasound and fluoroscopy, and interact and exchange information with medical teams during tumor boards or similar meetings. Only robots would be able to do procedures and interactive imaging studies, but we're nowhere close to building such complex robots. Note that all these tasks not involving the interpretation of images make up only a small portion of a radiologist's time, and there's limited demand for other activities of radiologists. If AI ever replaces the imaging interpretation performed by radiologists, then their demands will be highly reduced, but not completely eliminated. Important issues are FDA approval and legal liability. Medicine is still an art, which will never be fully quantified, and will be difficult to fully impart to computers. But the FDA already allows many medical activities to be performed unsupervised by machines if they are well tested. For example, most laboratory tests these days are fully automated. They can influence life or death decisions, but the FDA allows them to be performed and interpreted without physician supervision. The FDA has already approved the unsupervised interpretation of ocular images by AI algorithms. AI will never be 100% accurate. In cases of inaccuracies, the legal responsibility will need to be determined. This is still unbroken ground, but already approved AI algorithms and devices will lead the way to determine how legal responsibility will be attributed. Here are the take-home points for this talk. First, Goeffrey Hinton's prediction of AI replacing radiologists within 5 years was way off by several decades, but it could still happen eventually, partly. Second, over these past 5 years, AI has made exponential progress. Billions of dollars are poured into the field, and thousands of researchers are working on the field. Third, AI will be a great help for radiologists, initially by handling simple, tedious tasks more consistently, like drawing contours and making basic measurements. With time, it will get better and will be able to handle more complex tasks. And fourth, there are still many limitations involved in the application of AI to medical imaging, but progress is being made every year. Thank you again for inviting me to give this talk.